had a subscriber that asked me if I had any resources for how to solve a two-dimensional non-homogeneous heat equation. And in terms of books, no, I do not. Besides the Waz book, which is a very, very good book on how to solve PDEs using various different types of methods. Other than that, the resource is this video. So I'm going to show you how to solve this problem in particular. And this down here doesn't necessarily have to be of this form. It can be of any form, but this is a relatively simple problem to solve. So this is the problem that I'm going to be working with here. And we don't necessarily even care too much about the boundary conditions. All we really care about with this method is the initial conditions up until the point that we want to verify our solution or that our system is consistent. Then we will care about our boundary conditions and all that stuff. But as for now, we don't really care about anything but the PDE itself and our initial conditions. So I'm going to be using the ADM, the Adomian decomposition method, to solve this problem here. And if you want a book on this method, the book by Waz, I've talked about this book on this channel before, is very, very good. It's a very awesome book. So right now, I'm going to just give you a brief introduction to this method. I'm not going to go too in-depth. I'm going to go a little bit quicker. And if you want a more in-depth view or discussion of this method where I go a lot slower, you can be sure to check out my videos that I've made on this method before. So we're going to start off this method by integrating both sides of our PDE here with respect to t, and our goal for doing this is to isolate our u term here. So let's go ahead and do that. So here, all I've done is used on the left-hand side anyways, all I've done is used our limits of integration. This is our upper limit, this is our lower limit. We are integrating with respect to t, remember? And here, all I've done on the right-hand side is integrated this part, extracted it, and this is what we have here. As far as this term right here goes, what I'm going to do is use our substitution here with our initial condition, where this is equal to xy, and I'm going to send it over to the other side. So let's go ahead and do that. At this point, we're going to begin with the Adomian decomposition method. So what this involves is using our inhomogeneous part here, or our non-homogeneous part, setting this equal to u naught, our first term in the series. Our next term in the series is going to be derived using the previous terms. So for instance, if we write down our new formula here, we're going to be using u naught, again, our previous term. Wherever we had the u's, we're going to write u naught to find the value of u1. And from this point, we can just plug our u naught into both of these partial differential operators. All I've done here at this point is carry out the integration, and we've derived our next value in our sum, which is u1. For u2, we do the exact same thing that we did for u1. So let's go ahead and rewrite the formula down. And we can plug our values in. And integrate. So this is our next value in the sum or the series. And because it doesn't have any x's or y's in it, it only has t's, we know that when we go to plug it back into our formula, like up above here, we know that when we take the second partial derivative of our u2, which is this one right here, right? When we go to take the second partial derivative of this function here with respect to x and y, we know that it's always going to be 0. So we do not have to continue with any terms in the series. But at this point, what we can do is just gather our terms and put them in series form, and let's see what we get. At this point, we're done with the problem. and this is the final solution. And of course, if you want to verify that your system is correct, this is where you would want to use your boundary, initial conditions, all that stuff. I haven't verified this problem for existence and uniqueness or any of that stuff. This is just a problem that I came up with off the top of my head, because again, I really couldn't find any resources for this, but you can very easily extend this method to uh, different types of PDEs. Again, doesn't really care too much about the homogeneity or the dimension. It somewhat cares about the linearity, but not all that much, as it can solve various different types of nonlinear differential equations. So yeah, this is the solution here, and I hope you found this video useful. That'll do for this one, guys. If you appreciate the content, if you like the content, be sure to like, comment, subscribe, share the video. We have Amazon affiliate links, and start on or plan on starting a Patreon. So yeah, that'll do it. See ya.